Section 16.6 on surface integrals. Okay, so what happened in our previous section? What happened in section 16.5? That's a terrible marker. What happened in section 16.5? We learned about parametrizing surfaces. And we used that to find surface area. So the idea was that if we had a surface S and a parametrization for it, R of u comma v, the surface area ends up being the double integral of 1 times the magnitude of R sub u cross R sub v, where those are partial derivatives du dv, and you're integrating over R the domain in the UV plane that corresponds to S here in 3 dimensions, X, Y, and Z. So this is what we talked about last time. We're going to generalize this in this section. So we're going to generalize the idea of surface integrals in 2 ways. So one is that we're going to have scalar surface integrals. And the idea here, we'll see this in just a moment, is that instead of integrating the constant 1, because that gives you surface area here, we're going to stick in some other function here. Some function f will go in here, won't be integrating f over the surface. We'll also learn about vector surface integrals. And in fact, the parallelism between scalar surface integrals and vector surface integrals should remind us in section 16.1 and 16.2 of the parallelism between scalar line integrals and vector line integrals. It should feel very, very similar. Okay, so before we get into the main part of this, I want to talk about parametrizations just a little bit. So sometimes we just have a generic looking parametrization R of UV, and there's nothing special that we can do here. In which case you would just go ahead and calculate R sub U, R sub V, the cross product of R sub U and R sub V, etc., etc., etc. We also talked about, in the previous section, spherical parameterizations. So that's a special case here. That's a special case, and we'll still be referring to spherical parameterizations in just a little bit. So here at the bottom, I have an entire sheet here that I'll show off. This is our spherical parameterization. We parameterize a sphere of radius capital R, oriented with an outward pointing normal vector, centered at the origin. So here is the R of phi comma theta right here. Here's the cross product. Here's the magnitude of the cross product. We also, in the last set of videos, learned about cylindrical parameterizations. And so this is going to be parameterizing a sphere, sorry, not a sphere, a cylinder with radius R centered on the z-axis here. And our parameters will do theta and z here. Here's the parameterization. Here's the cross product. There's the magnitude of the cross product. There's one more parameterization that we should talk about, and that is the graph of a function. So the idea here is that you have some function z is written as a function of x comma y. And so, here is, I guess I'm drawing some kind of upper opening paraboloid here. So z is equal to some function of x comma y here. And so our parameterization that we'll use in this case will be, we'll index things, we'll parameterize things with x and y. X is just x, y is just y, And then the z coordinate is whatever is the function of x and y here. And then you'd integrate over some region in the xy plane that would correspond to the shadow of the region that you're talking about. Okay, so r of x comma y here is x, y, f of x, y. Let's figure out what's the cross product of the partial derivatives, what's the magnitude of the cross product of the partial derivatives. And so the partial derivative with respect to x here, 1. Partial derivative of x with respect to x is 1. Partial derivative of y with respect to x is 0. And then the partial derivative of our function here, let's just write f sub x, the x partial derivative. Partial derivative with respect to y is going to be 0, then 1, and f sub y. And now to find the cross product here, r sub x cross r sub y is going to be, okay, I hat, j hat, k hat, 1, 0, f sub x. I'm just filling in these entries right here. 0, 1, f sub y. And if you crunch out everything here, this ends up as the negative f sub x partial derivative, the negative f sub y partial derivative, and 1. So this is the cross product of the partial derivatives. We also will care about the magnitude of the cross product here. And so it's going to be this squared plus this squared plus this squared. This squared is just 1. Negative f sub x squared is just positive f sub x squared. And then positive f sub y squared here. This is the magnitude of the cross product here. And so let me bring this sheet back on and leave it a little bit longer and show you everything here. So these are our 3 main types of parameterizations that you need to know, other than just a general case. It could just be some general case R of u v where you have to calculate everything from scratch here. But either in the last section or in this section here, we work through together how to find all of these parameterizations for the spheres, for a cylinder, for the graph of a function, part of a graph of a function. And we also turned out in either last section or this section, the cross product of the partial derivative vectors and also the magnitudes of the cross products. So in this section and future sections, we're going to be using this sheet a lot because whenever we have a sphere of radius r, a cylinder of radius r, graph of a function, we can just refer to this sheet to very quickly write down what are the parameterizations, what's the cross product here, what's the magnitude of the cross product. Whatever we need, we can get it very quickly from the sheet.